So let's jump in. So today we're going to be talking about adiabatic and isothermal expansions and compressions, but the adiabats are the new ones. You'll have done isothermal expansions and compressions. You've got the work equation for that, and so it's pretty easy to do. But let's talk about adiabatic expansion, because the adiabatic expansion is unique in that it's not iso anything. The only thing that it does is typically happens so rapidly that there can't be any heat exchange. So that since there's no heat exchange, the temperature changes when it expands. Okay. So here we have this comparison of isothermal versus adiabatic expansion. And so if we want to maintain the same temperature, we have to put in heat to expand isothermally. So that adding of heat, because it keeps the temperature the same, it also keeps the pressure higher. Because we're putting in heat, we're expanding, it would tend to cool. The pressure does drop, but it doesn't drop as much as it would if it was to expand and change temperature. So let's look at this. Adiabatic means no heat flow. So that's what we mean by that, no heat flow. So we know here that Q is equal to 0. And so how do we, characterize this? Well, if we look at this PF over PI, let's go ahead and write it a different way. So PF over PI is equal to VI over VF. So this is like that, combined gas law type thing. And this is to the first power. You see that? Okay. And here we have this one, PF over PI is equal to VI on top over VF. And this is to a power called gamma. So it's not 1, it's some number greater than 1. So we'll see what that number is, but it's a number greater than 1. And so what does that mean? That means that the pressure final, you see, if this ratio, which is less than 1, if we're doing an expansion, right? If this ratio is less than 1, and I raise it to a power that's greater than 1, it gets even smaller. So it's like 1/4 or 1/4 squared. Okay, if I raise it to a bigger power, it's a smaller fraction. And so then the pressure final is a smaller pressure. Okay, does everybody see that? If gamma is greater than 1, then we have a bigger drop in pressure, a smaller final pressure. So this is PF for the adiabat, this is PF for the isotherm, if we're looking straight on to the pressure volume plane, if they all start at the same PI. And so for this, both of these, this delta V is the same. So this is the same delta V. So for the same expansion, delta V expansion, PF is lower for an adiabat than it is for an isotherm. This is important if you see a cycle and you see a couple of curves that are smoothly varying. You need to identify which one's the isotherm and which one's the adiabat. So the adiabats are steeper. Okay, so that's another thing that you need this for. So how do we determine what that final temperature is? Well, if we know the delta V's, we can rearrange these things, and we'll do some algebra here in a minute to show how these relationships work. But gamma, here's the definition of gamma. It's CP over CV. And since CP is equal to CV plus R, then the numerator is always greater than the denominator, and so CP is always higher than CV, and so this gamma is always greater than 1. And so that's how we can be confident that that pressure curve is steeper for adiabats than it is for isotherms. Okay. Now, if Q is 0, remember that delta U is equal to Q plus W, and Q is equal to 0, therefore delta U is equal to W. So the bigger the temperature drop, so this piece is number of moles times CV times delta T. So if delta T goes up, work goes up. So the magnitude of that change, temperature change. Now, if delta T is negative, if it's bigger negative, then work is bigger negative. So they both go in the same direction. So what I want to get more work out of my system is a bigger change in temperature. We talked about that before too with the Carnot cycle. We had the temperature cold and temperature hot. We want those to be as far apart as possible. So the adiabatic expansion is really a key part of these processes. It's what's driving those temperatures apart. Okay, so let's look at some of these relationships. So far, we've got a relationship of pressure to volume. Let's show you where this temperature to volume relationship came from. Okay, and also let's show you where these relationships, if we start with the first law, again, we have that Q is equal to 0, and we have this, again, pushing against some external pressure that's smoothly changing. And so what we're going to do is integrate both sides. The left side will integrate with respect to temperature, and the right with respect to volume. Okay, these both look like the natural log. It's the derivative of natural log here. So if we integrate it, we get that natural log back. And so on the left, for this adiabatic expansion, we have N times CV, natural log of Ti over Tf. And on the right, we have minus Nr ln Vi over Vf. Now, in your little notes, it has A's and B's. Now, I went through this morning very tedious and careful, swapping all those little A's and little B's to F's and I's, okay? Because in the past, again, I'm trying to correct things that I saw that misled students in the past. When we go, I was just using A and B to just pick two different volumes. I called one A, one B. But then when we get to the Carnot cycle, we have 4 points, A, B, C, and D. Now, they're capital A's and B's, but a lot of students were thinking that when I had A's and B's here, that it was the Carnot cycle A's and B's. And that's not correct, okay? And so trying to get students to not connect the A's and B's on this slide to the A's and B's 5 slides later on the Carnot cycle was a problem. So I went ahead and changed it to F's and I's. Okay, so in all of these little ones, these relationships, it's just final and initial. And so this will work for compression or expansion for your adiabats. When you compare it to the Carnot cycle, the actual adiabats are the B to C lines and the D to A lines, traditionally. Those are if you start in the upper left-hand corner on the Carnot cycle, and you'll see it's A, B, C, and D. So don't be bothered by me swapping those things. I just sort of made it more generic. It's to initial and final. Okay. So if we look at this, what's the difference between CP and CV? It's essentially R, right? That number of moles times R. So this piece right here, the number of moles can cancel on both sides. So we have CV over here, and we have CP minus CV over here. And then we have this natural log. And I've also gotten rid of the minus sign by swapping final and initial. Okay, so here, that's where the minus sign went. Does everybody see that? Okay. Now, I can divide both sides by CV. And so divide both sides by CV, I end up with a CV under the CP, and I have a CV under the CV. So that's gamma minus 1 there. So gamma minus 1. And so if I make that over here as an exponent, then the natural logs can cancel. Okay. And so I just move this over to the exponent here. And that's where that relationship to temperature comes from. So this would be if I know the final and initial volumes, and I know that type of gas, I can calculate gamma, then I can tell what kind of temperature difference I'm going to get. So that's a really good relationship. And finally, we get to see a 3-dimensional phase diagram here. So this is for gas. So these are our working fluids. Almost always when we're pushing pistons and so on, we're using gases. So all of our combustion engines are using gases. Our refrigeration units, when we cool and heat things, our heat pumps are using gases. That's what the refrigerant is. And then even gas turbines, there's a compression cycle and an expansion cycle in a gas turbine. It's just kind of strange because the reactants flow through the turbine. Like they're not captured like they are in a piston. but you still have a compression step and an expansion step, and you still get work out of it. It's just that the reactants and products flow through it. And it's just more conceptually difficult for me, at least, to see a gas turbine as a heat engine, but it is also. And so what we see now with this three-dimensional phase diagram, we can see that this is a steeper descent. You see, we're going sort of down the steepest part of the hill, whereas if we're an isotherm, we're adding in heat and kind of following it along this particular temperature. So the isotherm is like this slice through the PVT diagram, whereas an adiabat, it just falls straight down the hill. And so we're changing temperature too as we expand. Okay? And we're increasing temperature as we compress. We have adiabatic compression too. Okay. So now we can take this relationship, we can manipulate it around. If let's say we have the temperatures and we want to find the volumes, okay, we can take both sides to the 1 over gamma minus 1, right? If you wanted to get rid of the square, you would take the square root. Well, the square root is taking it to the 1/2 power, and they would cancel. And then you'd have the same thing on the other side. So the 1 over gamma minus 1, this one doesn't cancel with anything. So that's how you get the powers onto the other side. Just a review of algebra and your exponents, okay? So these guys cancel here. And so you have the VF over VI to the first power, and then over here you have temperature over 1 over gamma minus 1. Now these are really ugly, but they're not a problem to work with. I mean, once you find gamma, you just subtract 1 and invert it, and you've got your exponent. Okay. Now, one thing we can do if we wanted to get the pressure-volume relationships, we could substitute instead of this volume here, V final and V initial. We can put in, again, this relationship where we have the PI, VI, NI, and so on. Well, NI and R are constants. Okay. And so here we've got, so we've solved for temperature. So PV equals nRT. So if we solve for temperature, we end up with PV over NR. And so we've put that in here. And so we're going to substitute that in to this top equation. So up here, this TITF is going to be these pieces. So the NI and the R's and the NFs and R's, they cancel. We haven't changed the number of moles. And so we have this relationship on the left. So we have PI times VI. I just drew my parentheses a little differently. And that equals to this VF over VI to the gamma minus 1. So it's this top relationship here. And now I've got volumes on both sides. And so what am I going to do with that? Well, I'm going to multiply both sides by the inverse of this. So I'm going to say VF over VI. So these cancel on this side. Everybody agree with that? Do the same thing to both sides of the equation. And now I have this thing raised to the gamma minus 1 power, and then it's multiplied by another one of those things, which adds one of those powers. And so I end up with just gamma there. So that's our pressure-volume relationship. It's just raised to the gamma power. So now we have the relationship of temperature to volume. We have the relationship of pressure to volume. We could get the relationship of temperature to pressure. So we could have all of these relationships here. Here's temperature to volume, here's volume to temperature, here's pressure to volume. Now let's talk about gammas. So this gamma is required for this use of these adiabatic relationships, and so it depends upon what kind of gas we use. Just to reinforce that isotherm has a gamma of 1. And so if we start with a particular PI and we follow that down, this would be an isothermal expansion. Okay, gamma equals 1. Okay, let's look for helium. So Cp over Cv, Well, we know CV for helium. So if we're for finding gamma, go to CV first. And for a monatomic gas, we have 3/2 R. We only have translation. Is everybody okay with that one? That's that CV calculations that we were doing. And we got really good at that, right? And so then the CP is just one more R. So if we're dealing in halves, so add 2 more halves and you got the numerator. So then go up to here, you've got the numerator. Notice that the half R's cancel and we end up with 5/3. So that's gamma for a monatomic gas, 5/3. Everybody see the procedure? Do CV first, add an R, and then simplify. Okay, for a linear molecule like CO2, we do gamma first. So we have translation and rotation. It's a linear rotation, so we only have 2 halves for the 2 degrees of freedom of rotation because it's a linear molecule. So we end up with 5 halves. Then we add another 2, so we have 7 halves. The half R's cancel, and we end up with 7/5. So that's the gamma for CO2. And then for water, why do we only have, and we didn't use the vibrations, right? So we just use the translations and the rotations. Okay. And that, why do you think that is? Can y'all explain it? Yeah, so how would we track if those things are active or not? You had an energy, but what's another way to get more energy into it? What would you track? Yeah, temperature. So is there not a high enough temperature to activate those vibrations? You're right, it's the energy, but we track it with temperature. So it's not at a high enough temperature. Even in a gasoline engine, it's not really activating those vibrations, or a steam engine. So this would be the probably the most reasonable one. So then we have 6 halves. We add another 2 halves to get CP. Those cancel. We end up with 8/6 or 4/3 or 1 1/3. So remember, this is the exponent of that fraction of VF over VI. Okay. And so this one here, I'm going to try to get all 3 of these on here. This would be gamma equals 1.33. This one, I won't say that it's to scale, okay? Gamma equals 1.4. Gamma equals 1.67, okay? Now looking at those 4 curves, the isotherm, the gamma for water or steam, the gamma for a linear molecule, nitrogen, oxygen, CO2, or the gamma for a monatomic gas like helium, neon, argon, which of those is going to be a lower temperature? They're all at the same volume, or I tried to draw them at the same volume. And you can see their pressures there. Which one is going to be at the lowest temperature? The helium one, yeah. The one that's got the lowest pressure, because how did you get a lower pressure? You cooled it down. You're at the same volume, so the only way to get a lower pressure is to drop the temperature. So that one has the largest change in internal energy, is the one that has the lowest temperature. Okay. So let's do a top hat now. Oh, goodness. So for a given adiabatic expansion, which working gas produces the most work? Okay, let's see what we got. Okay, we got a split. I guess it's going to either be one with the largest gamma or the one with the smallest gamma. Okay, so it's a monatomic gas. Okay, so the next question, why do monatomic gases produce more work upon the same delta V expansion? And this is a discussion question. So you guys are fast at texting and typing with your thumbs. So have at it. You're going to be anonymous to your peers. So. But your answers will come up here so we can have a nice little view of what you got here. You got an unfair advantage. Very good, very good. Say again. Oh, I like that one. The greater difference in CP and CV. That's what I would like to clue in on. So that's great. You're right. You would get a different temperature, but it's related to that CV value as to how much energy change we have relative to the change in temperature. And that is that heat capacity. All right. Very good. So I've got plenty of answers here. So let's discuss. Okay, so let's think about what's going on with these heat capacities in terms of helium and CO2 and water. So when we do work, we're talking about expansion work. Let's make it as simple as possible. Let's push a piston, okay? So if I put some joules into a gas molecule to make it push a piston, what's actually going to push the piston? Is vibration going to push the piston? Is rotation going to push the piston? No, translation is going to push the piston. And so thinking about that monatomic gas, all it can do is translate. So every joule of energy I put into a monatomic gas will go into translational motion and push that piston. It has the smallest heat capacity. Okay, so it has a huge change in temperature whenever I change the energy. And so that's what pushes those temperatures apart, but that also makes it the most efficient gas for pushing things because there's no squishiness to it. Rotation is a squishy thing. I put energy into a molecule and 2/5 of it go into rotating. Okay. And only 3/5 goes into pushing things. Okay. And water, half goes into rotations and half goes into translations. And so water's really squishy. And not only that, it has those hydrogen bonds and everything. So even the molecules kind of stick to each other, which is not calculated in here, but that's a problem too. Okay. So yeah, that's the best working fluid would be a monatomic gas. And so our coolest refrigerators, you can also do this too, for a given change in internal energy, like a given pressure, volume expansion, a given volume pressure expansion, which drops the temperature the most? It would be a monatomic gas. And so we use helium for those really cold temperature refrigeration cycles. And so that's really good. So anyway, it's just good to think about those degrees of freedom and the heat capacity. And if I want to push something, I really want translation. And the more complicated the gas, the less of the proportion of energy is going to go into translational motion. And it's going to be even worse if I have a really big floppy molecule and I start activating some vibrations. Then I'm even losing more translational motion at the expense, and getting more vibrations at the expense of what could go into velocity and push power. Okay. All right. So here's our Carnot cycle, and here's the state variables table for the Carnot cycle. And now you can see the A, B, C, and D that I was talking about. Yeah, so in your notes, those little A's, B's, and C's, they don't correspond to these big A, B's, and C's. Okay, that's why I switched them to T final and T initial. So we have here some isotherms that are solid lines, and so you can see the isotherms are here and here. And then these dashed lines are the adiabats, the steeper ones, here and here. So A to B is isothermal, and C to D is isothermal. And then B to C is an adiabat, and then D to A is an adiabat. This is kind of ugly, I know. Okay. And you can see that over here, but that's the key for finding out, which of these is hot and cold. You see both A and B are on an isotherm, so they have the same temperature. And then C and D are on an isotherm, so they have the same cold temperature. The farther apart those two lines are, the more work I get out of the system. Now, in real engines, we typically know the largest volume and the smallest. And the displacement is the difference between those two. So VC minus VA, that's the displacement. So when we talk about my truck, a 5.7 liter engine, that's the displacement of all 8 cylinders added together. Okay, so we just take all of those. So take 5.7 divided by 8. That's how much volume is being displaced by the pistons in my truck. Okay. And then we also need something else to get, because we have one equation and 2 unknowns, so we can't really solve for VA and VC. But if we know the compression ratio, there's our second equation. So typically we'll know the compression ratio, which is at VC over VA. So, how much we compress it. If we have a large VC and we have a really small VA, then we have a huge compression ratio. Sometimes these are like 150. So if I've got a 5.0 displacement and I know my compression ratio is 150, then I can figure out what VA is and what VC is. So let's do that math. Okay. So here's our compression ratio. Here's our displacement. And so we can rearrange this. We can solve for VC by multiplying both sides by VA. So we bring that over here. So we have VA times the compression ratio. And so we can put that in for VC. So this is the displacement equation. And we know the compression ratio. We know the delta V. So we can solve for VA. So VA is that delta V divided by the compression ratio minus 1. Okay, so there's our volume A. again, a small volume. So if like I had 150 to 1 compression ratio, then I could put that in 150, so it'd be 149. So 5.7 liters divided by 149 would be my volume A. Okay. Let's see. 150 is a little high. I was thinking pressure in terms of, here's one from a website that if you wanted to modify your cylinder size and bore it out and so on, here's a compression ratio 8.4 to 1. Okay, and so it's an online calculator for people who want to modify their engines. Yeah. And then what?
On our notes, it's the VC is equal to delta V minus the delta V over up there. It's delta V plus the delta V over.
Oh, really? That's weird. Where is it again? Which one?
It's the last one.
This one here should be a minus there. Okay, let's see if that makes sense. Where are we? So we have this. Yeah, so we've plugged in VA here. We took this piece and plugged it into VA. Okay. And then we added it to both sides, so it should be a plus. VC is delta V plus VA. See that? Yeah. Yeah. So that should be a plus sign. And so that tells us, we have VA here, then we add the displacement and we get VC. So once you have VA, then you can add the displacement and get VC. So again, we could take this, like this is cubic inches here for this Trans Am, 400 cubic inch engine, and here's the compression ratio. So we could figure out what the smallest volume is and what the largest volume is for this engine. And so using those two equations, we can get VA and VC. What are we going to do in terms of our assumptions? The initial assumption would be that these would be 298 room temperature, although they're going to creep up as the engine gets hot. Then this is the real question: how hot are the combusting gases? So we really don't know that. Okay. But if we made an assumption on those, then we would have our VC, our T cold. We could calculate our pressure here. And if we made an assumption for our hot temperature, we could calculate our PA. So notice how it's pretty straightforward. If I know my hot temperatures and my cold temperatures, and I calculate the VA and VC from my compression ratio and displacement, I can get my pressure points. So I can easily get A and C. Somebody see that? Ideal gas law, no gamma, it doesn't matter what gas I've got. Okay. The real trick is trying to solve for B here and D. These are the ones that require the adiabatic relationships. You see here, this is, if I've got my temperatures, I can use this adiabatic relationship to get my volume B. And so here I am, this is connected, so the volume B is connected by an adiabatic relationship with C. So since I know volume C, and I know the temperature at C, so this is the temperature at C here, and the temperature at B is here, and I know gamma because I know what kind of gas I'm using, then I can solve for VB. But notice which point I use. This is another place where people mess up. They use volume A here instead of volume C. And volume A is on an isotherm with B. So we're not supposed to use volume A. We're supposed to connect B to C with this adiabat, because that's the relationship for an adiabatic expansion. And so when I'm grading your problem that you do for the Carnot cycle, I have to see you use the adiabatic relationships or you did it wrong. So if I don't see that math on there, I'm just like, well, they didn't use the adiabats, and so they got it wrong. Okay. I mean, I could look at your final result too, but this will tell me where you went wrong. Okay. Now, if you were to calculate the volume of B using the wrong one like A, you might end up with like a volume up here or something crazy like that. And that's where you need to compare it to the chart. Okay. And so if you use the wrong volume and you get a wonky result, You won't know it unless you look at the chart and say, does this make sense? Your smallest volume is VA and your largest volume is VC. And so if you get any volume outside of those, you know it's wrong. Makes sense? Yeah. Now, sometimes if, if you're in a different pressure temperature region, sometimes volume D will be down here and volume B will be up here because this curves are really steep. And so B can be less than D. They can just hit these top two curves at different places. And so it's not a hard and fast rule that B is larger than D. Look at the two volumes. B can be smaller than D. It's still higher temperature though, but it's just slid up that curve a little bit. But you do know B and D have to be between A and C. So you can just look at your table. If you're getting a V value that's not between A and C, then you got it wrong. And then you do the same thing down here, only for D, notice it's connected to temperature A. Okay. And if you don't get a D value that's between A and B, you've done it wrong. So these are the kinds of things that you just check yourself with. They come from experience, right? If you do these wrong a while, you say, oh, well, what was my error? What could I have checked? Well, one thing you can check is that volume B and D have to be between volume A and volume C. And then you can calculate those pressures at those two volumes using the ideal gas law. Now, we could have used the pressure volume relationships. If we have pressure at C and volume at C, pressure at A, volume at A, we could use the adiabatic relationship for pressure too. But once you know two of the three variables, you can calculate the third with the ideal gas law. Okay. But you have to use the adiabatic relationship, either volume and temperature or volume and pressure, and either one will work. So, and then once you found let's say you did the pressure route and you found, you would use, in that case, temperature and you would use temperature and pressure to get pressure, and then you would use the ideal gas law to get the volume. Yeah. Okay. Let's go ahead and write that one on here so we can see what I'm talking about. So is there a temperature pressure one? Have we defined that one? I don't guess we did. So I guess I was just gearing it up for you to use the pressure, the temperature volume one. So okay, well, never mind then. Okay, so that's the Carnot cycle. Next time we'll walk through and actually solve all of those legs. How much work was on the isotherm? How much work was on the adiabat? And so we'll do all of that. We'll calculate the efficiency, and we'll do the whole cycle problem. Okay, so be sure to come bright-eyed, ready to do some algebra, and it'll be great. See you then.